Hello, calculus students. All right, this is part 2 of section 10.3. We're going to keep working with parametric equations in calculus, and we're going to move on to basically anti-differentiation today with parametric equations. And we're going to start by finding arc length. And all the things we do today are things you've done before, but we're just going to do them with parametric equations. All right, so we'll start with finding arc length. So if a smooth curve C is given by x equals f of t and y equals g of t, two parametric equations, such that C does not intersect itself on the interval a is less than or equal to t, which is less than or equal to b, except possibly at the endpoints, then the arc length of C over the interval is given by, well, integrating from a to b, and then finding the integral from a to b of the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. And then don't forget your dt. All right, that's the same thing as doing the integral from a to b of the square root. We can also write this as f prime of t squared plus g prime of t squared. So whichever one you prefer, you can write. I kind of prefer the first version, but it's up to you. Now, we want to revisit the definition of what the heck is a smooth curve. And remember that a smooth curve is, well, it's defined. I guess the characteristics we really need to keep in mind when we're determining if something is a smooth curve is that, well, it's smooth if f prime and g prime, if we have these parametric functions, are continuous on some interval. Continuous on some interval, we'll call it I. And more importantly, they are not zero simultaneously on that interval. So that's what you have to keep in mind for, I guess, the first part of finding arc length. Is it a smooth curve? And then this is how you determine if it's a smooth curve. If f prime and g prime are continuous on some interval, and they're not simultaneously zero on that interval. All right, so let's move on to an example. A circle of radius 1 rolls around the circumference of a larger circle of radius 4. The epicycloid, that's the name of what we're making here, traced by a point on the circumference of the smaller circle, is given by the set of parametric equations x equals 5 cosine of t minus cosine of 5t, and y equals 5 sine of t minus sine of 5t. We want to find the distance traveled by that point in one complete trip about the large circle. So we're starting here, we're going this way. Basically, we want to find that distance there. Okay, now there's a couple things we want to note. We know that, well, each trip here is going to be the same distance. So really, it's the same. The problem is just basically asking, what is the distance of one of these arcs, and then we multiply that by 4. Okay, well, let's take that into account. How do I find the length of that arc? And if you notice, there's a couple different things we can do here. Well, once again, we need to find what are our values of t at these given points. We know that this is a value of 0, 4. We know that this is a value of 4, 0. And using previous techniques, we can solve for we can solve for t. So if I let x equals 0 here, well, I'm really saying 0 equals 5 cosine of t minus cosine of 5t, or I'm really saying, where is cosine of 5t equal to 5 cosine of t? And there's a couple different answers you can come to, or you could conclude that it is, well, an x value of 0 yields a t value of pi over 3. T equals, or not pi over 3, it should be pi over 2. Sorry. Thinking about the next problem. Pi over 2. And you could plug in 4 for x again, solve that again. Or it'd be easier if you plug in 0 for y. Essentially, if you plug in 0 for y, you're asking the question, where is sine of 5t equal to 5 sine of t? And that's going to be true when t equals 0. Okay, so we can solve there. And now that we have our t values, we know that our interval for this specific part is going to be t is greater than or equal to 0, but less than or equal to pi over 2. You could also notice, well, this is literally the first starting point to the second, I guess, the quadrant of a unit circle. And that's interesting how that works out because, well, we're really literally just starting at this point of a circle and then working 1/4 of the way this way of a circle. So you could also keep that in mind. instead of having to solve for x and y, you could have just realized that. All right, so we know that this is going to be the distance of one arc length. We'll multiply that by 4. So our total arc length around this whole circle is going to be 4 times that integral. We're going to be going from 0 to pi over 2. And then I'm just going to rewrite this. We want to do the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. I'll just rewrite that. dx dt squared plus dy dt squared dt. All right, so rewrite a couple things, but then just evaluate some things. All right, the derivative of x with respect to t, well, we're going to get 5 cosine of t. That becomes negative 5 sine of t, negative 5 sine of t. Then negative cosine of 5t, that's kind of like a chain rule. So we're going to get negative, and then we multiply by the derivative of the inside. So we're going to end up with positive 5 sine of 5t. We're squaring that. Plus the derivative of y with respect to t. So that's going to be 5 cosine of t minus. And then the derivative of sine of 5t is 5 cosine of t. 5 cosine of 5t. Square that, dt. Make sure this is all under that radical there. All right. So we kind of have a beastly binomial to expand here. But just remember, when I'm squaring a binomial, it's the first term squared plus 2 times the product of the first and second term plus that last term squared. So I'm going to have negative 5 sine squared, which is going to give me 25 sine squared t. I'm going to have 2 times the product of the first and second term. Well, that's going to give me negative 25 times 2, so I get negative 50 sine t sine of 5t. Plus that last term squared is going to be 25 sine of 5t squared. All right. Then I'm adding this part. We're going to expand this binomial now. And that should give me 25 cosine squared of t minus, again, 2 times the product of those things is going to give me minus 50 cosine of t cosine of 5t. And then lastly, that last term squared is going to give me a positive 25 cosine of 5t. All right, and don't forget this is all underneath a radical, which is what makes this tricky. All right, dt. Simplify some things here. Okay, now, we know that sine squared plus cosine squared equals 1. So if I have 25 sine squared plus 25 cosine squared, that should be, well, 25 of those. So it should be 25. So this plus this is going to give me 25. Okay, now we also have 25 sine squared of 5t, and we have 25, 25, this should be 25, I missed a thing. This should be 25 cosine squared of 5t. Okay, so if I have cosine squared of some angle value and plus a sine squared of another angle value, I add those together, it should be 1. And if I have 25 of those, it should be 25 then. So this part right here that I'm going to highlight in light blue, 25 sine squared of 5t plus 25 cosine squared of 5t, add those together, that's going to be 25. So really, I can rewrite this. This is going to equal 4 times the integral from 0 to pi over 2, the square root of, well, these yellow values combined to be 25, those blue values combined to be 25. 25 plus 25 gives me 50. So I have 50 minus 50 of sine t sine of 5t plus, or excuse me, not plus, minus another 50 of cosine of t cosine of 5t dt. And what we can do here is notice that all these terms have a 50 in common. We can factor that out. So that'd be like the square root of 50 times the square root of 2 minus 2, blah, 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 blah. Or, excuse me, not 2, whoops. I guess we could factor out a 50, but we want to factor out a perfect square because, well, if we notice they all have a 25 in common, factor out a 25, I can evaluate the square root of 25. We're going to do that rather than factoring out the square root of 50, because now we're going to be left with, technically we'd be left with 2 minus 2, so on and so forth. But what is the square root of 25 going to be? What type of thing? It's a constant, so I can just multiply that constant out front with that 4. So the square root of 25, that's 5. This is the same thing as saying 4 times 5. Well, that's 20. Then I'm integrating from 0 to pi over 2. And keep in mind, we've just factored out the square root of 25, which is going to leave me with, well, 2 minus 2 sine of t sine of 5t minus 2 cosine of t cosine of 5t dt. All right. So what we're going to do next here is kind of just simplify some things, apply some trig identities. This is going to be equal to 20 times the integral of 0 to pi over 2 of 2 minus 2 cosine of 4t dt. And applying some trig identities, we can simplify this down to 20 times the integral of 0 to pi over 2 of the square root of 4 sine squared 2t dt. Get this out of the radical. Now, we have essentially gotten to the point where we can evaluate this radical. Well, we have the square root of 4. That's the same thing as 2. Multiply that out front. 2 times 20 gives me 4 times, or 4d. And we're integrating from 0 to pi over 2. And then, well, the square root of sine squared 2t is just going to be sine of 2t dt. And now we can do some anti-differentiation rather easily. This is going to be the same as 40 times, well, what is the antiderivative of sine of 2t? Well, that's kind of reversing the chain rule. So we're saying what thing's derivative gives me sine of 2t? Well, we're going to have a 1/2 out in front because, well, we know that the derivative of the inside should just be 2, but we don't see a 2, which means that there must have been a 1/2. So we have to multiply by 1/2 out front, which leaves us with 20. We also know that, well, what thing's derivative gives me positive sine? We know that the derivative of cosine is negative sine, so it must have been negative cosine, which means we have to multiply a negative 1/2 out front, which will give us negative 20. We're left with cosine of 2t, which we are integrating from 0 to pi over 2. Plug that in, you'll get 40. Okay, so the arc length of this distance that we get when we revolve a circle around a circle is 40 units. And whatever we're measuring this in, it could be inches, whatever. That is our answer. All right. So that's just finding the arc length of something. We've done that before. Now we're doing with parametric equations. And this example is probably a little bit more complex than the ones you might see, but it's a good example. So we're going to move on to another application of integration that we've done before. Area of a surface of revolution. Think back to solids of revolution revolving about the x-axis, y-axis, so on and so forth. So we're going to apply that with parametric equations. If a smooth curve C, and keep in mind how a smooth curve is defined. Ooh, I want to revisit that. So I guess that was important. We had to know that this was a smooth curve. And we know that it is a smooth curve because we're going from 0 to pi over 2. If our functions f of t and g of t, remember x and y, or x is f of t, y would be g of t. We know that the derivatives of those are going to be continuous on that interval, and there's not going to be a single point where they are simultaneously 0. There's no value, and if you think of your unit circle, is there a value where I can go from 0 to pi over 2 where I will simultaneously get 0? And I guess you don't want to just think about it in terms of your unit circle. You want to say, is there any point where negative 5 sine of t plus 5 sine of 5t and cos 5 cosine of t minus 5 cosine of 5t, that's a mouthful, is ever going to simultaneously be 0? The answer is no. So that's how we knew it was a smooth curve. I guess I should have done that at the very beginning. But moving on, we want to find the area of a surface of revolution. So if we have a smooth curve, this is basically the same definition as before, where the parametric equations, or the smooth curve itself, does not cross itself on an interval a less than or equal to t less than or equal to b, except possibly at the endpoints. Or excuse me, not possibly at the endpoints. That's where the difference is. Then the area S of the surface of revolution formed by revolving C about the coordinate x-axis is given by the following. So we have these two cases. One is going to be used when you're revolving it about the x-axis. One's going to be used when you're revolving it about the y-axis. When you're revolving it about the x-axis for a parametric equation, it's going to be given by 2 pi, and this should look very familiar. And then we're going to have our limits of integration, a to b, times g of t times the square root of dx dt squared plus dy dt squared dt. Okay, now this is going to be revolving about x-axis where t is greater than or equal to 0. Excuse me, g of t. G of t is greater than or equal to 0. So remember what g of t stands for? If we're revolving this about the x-axis, in this next example we'll be doing exactly that. Remember, in the previous arc length ones, that value right here just represented our radius. It's basically our radius of this interval. And g of t is going to give us that radius. If we're revolving it about the x-axis, this g of t is going to give us our radius, if you want to think of it kind of like that. So it's basically the same thing. All right, now if we're revolving it about the y-axis, the equation is similar, but instead of my radius being g of t, it's going to be f of t. So it's given by 2 pi times a to b of f of t, and then everything else is the same, times dx dt squared plus dy dt squared dt. And this is if we were revolving it about the y-axis. And f of t is greater than or equal to 0. All right, so we'll move on to an example here. Make sure you get those definitions down. Finding the area of a surface of revolution. So if C is the arc of the circle, x squared, this should be x squared plus y squared equals 9. X squared plus y squared equals 9. You should recognize right away that's the formula for a circle where we have a radius of 3. Okay, now we are going from 3, 0, right here, this is our starting point, to 3 halves, comma 3 root 3 over 2. We want to find the area of the surface formed by revolving C about the x-axis. All right, so what we want to do is, if we want to do some parametric equation stuff, is we need to have parametric equations. Well, how can I represent two equations? We should have x equals something and y equals something. And keep in mind, well, how the heck can I get this in terms of a parametric equation? And think, well, since this is a circle, there's a couple things you can do here. We are saying x equals 3. So x equals 3 here, and x equals 3 halves here. We're saying, what is our value for t when x equals 3? What is our value for t when x equals 3 halves? Now, coming up with equations seems like it would be a difficult thing to do, but this is a circle. So coming up with an equation actually isn't too bad. If we want to come up with an equation for our x values, well, we have a circle here, and we're starting at the point 3, 0. If we think of our unit circle, where does that usually start? It starts at 1, 0, right? So kind of we're just going to multiply everything by a factor of 3. This is our x value. We can get a parametric equation. It's just going to be 3 cosine of t, and our y will be 3 sine of t. So really, that's not too bad to come up with. Now, we have to come up with our interval. What is our interval for t? Okay, so what we have to keep in mind here is this is what I was kind of talking about earlier. If x equals 3, now that we have our equations, just plug it in. When is 3 equal to 3 cosine of t? Divide by 3. You'll find that at this point, t is going to equal, well, when is cosine of t equal to 0? And the answer is at 0. So t equals 0. Okay, we're saying when is, well, if we plug in 3 halves for x, 3 halves, divide by 3, that's the same as multiplying by 1/3. That's 3 over 2 times 3. That's 3 over 6, 1/2. So when is cosine of t equal to 1/2? And the answer is at pi over 3. So those are our limits that we've just set up on this value. This happens when t equals pi over 3. All right, so we have our limits of integration. We want to find the surface area. All we're going to do is plug things in and do some calculus. So this isn't too bad. Surface area is going to be 2 pi times, now we're integrating from 0 to pi over 3. And we want to find the arc, or the surface of revolution, when we revolve it about the x-axis. So use that first equation when we're revolving about the x-axis. Well, that's 2 pi times g of t. Well, that's just going to be 3 sine t. Times the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. Well, derivative of x is going, with respect to t, is going to be negative 3 sine t, we're squaring that, plus the derivative of 3 sine t with respect to t is just going to be 3 cosine of t squared. Simplify this, it's equal to 2 pi, 0 to pi over 3 of 3 sine t. And now that 3 is being multiplied out front. That is a constant multiple. We can bring that out. That's the same as doing 6 pi times sine of t, square root of, simplify these things, negative 3 sine t squared is just going to be 9 sine squared t, plus 3 cosine t squared is going to be 9 cosine squared t. And we should be able to recognize this is just going to be 9. So I have 6 pi times the integral of 0 to pi over 3 times sine of t times 9 sine squared t plus 9 cosine squared t is going to give me 9. Square root of 9. Well, that's just 3. So, I don't want to forget my dt's here. I did that. Square root of 9 is 3. I can just bring that out front again. This is going to be 18. 18 times sine of t. All right. This part's pretty easy. Do the antiderivative. What derivative gives me sine of t? Well, we know cosine is negative sine, so it must have been negative cosine. So bring that negative out front. Negative 18 pi. We've done our antiderivative. Now we just need to plug in our values. We have the antiderivative is going to be negative cosine of t, but keep in mind we brought that negative out front. So just cosine of t from 0 to pi over 3. Plug those values in. You're going to get negative 18 pi times, well, cosine of pi over 3 is 1/2, minus cosine of 0 is 1. And we're just going to be multiplying negative 18 by negative 1/2. We get positive 9 pi. That is the surface of revolution. And that's, I guess, already been found for us. And we verified that. All right. So that's all we're going to tackle today. That's the end of these section of notes. Basically, we're just doing integration and stuff like that, like you've done before, but with parametric equations. All right. That's all we're going to cover today. Have a good day, everybody. And as always, stay safe out there.